Hello everyone, today we will be diving into our fascinating world of modern physics. Our presentation focus on a thought-provoking scenario involving space travel and relativity. My name is Muhammad Zaki Al-Bukhari, and together with my team,
My name is Yanto Rahmat.
My name is Abin Fakhri Arif.
My name is Mahija Nathaniel Sambarana Rentawira Mohede.
My name is Aryan Putra Tayala.
and we will explore the effect of high-speed travel on measurement of length. Next slide, please. So the background story is the astronaut aboard the spacecraft flight speed 1 are on a mission to Alpha Centauri. The ship is moving at 0.95 relative to a space station. Commander Alice on the ship and Officer Bob at the space station disagree on the ship length. Bob claimed that the spaceship looked compressed from his perspective. But in Alice, however, insists the ship length is the same. Who is correct and why?
Yeah, and these are our tasks. We have four for the task and four for the guiding questions that talks about the POV of Alice and Bob and how they disagree on the ship's length. And also we calculate about the length contradiction of the ship itself when looking from two point of views. And there's also a study case on the guiding question will be answered in the next slide. Okay, so how does motion affect measurements of length? So the proper length of the spaceship is length measured in the object's own frame. So we see it as like let's say 100 meters. Meanwhile, Alice measures the proper length and Bob measures the contradicted length because of the different location. While Alice is in the ship, she sees it as 100 meters, but Bob, because he's on the station that's far away from the ship, he sees it as at least like 30 meters. And what is the proper length of the spaceship and who measures it? The motion of effects measurement of length due to contraction is a concept of Einstein's special relativity. As we were mentioning earlier, the fact that Bob and Alice sees it differently. They measure it differently and they see it differently. And the next question will be answered by the next person.
So as we know that length contracts as we get closer to the speed of light, as we can see from Lorentz transformation equation over here, that if the spaceship was to move at a speed of 99% of the speed of light, where the original spaceship itself was 100 meters long, when we calculate this, the spaceship itself would only appear to be 14% of its original length from a standby observing person. The ship itself would only appear 14 meters long. Now, how does this apply to muons or high-speed particles or maybe even future space travel? Now, this would be very useful for future space travel, as we could shorten down the distances that we would have to go through, because going closer to the speed of light, as we know, can dilate the space-time itself. So it applies to future space travel, since astronauts traveling at relativistic speed would experience contracted distances, making interstellar travel seem shorter and more realistic. This is the same reason why, for example, in the Large Hadron Collider or maybe even muons coming to Earth, it should seem theoretically impossible for muons to come to Earth, since they only live for a few nanoseconds. But since they're traveling near the speed of light, the distance that they experience to reach here is shorter than the distance that it would take for a normal or an average object to come with a normal speed, not near to the speed of light. Next. So this is a space-time diagram, which is more commonly referred to as the Minkowski or the Lorentz diagram. As you can see that as we get closer to the speed of light in the left diagram, space and time itself actually dilates. So for example, here, maybe from our point of view, we see that they're going a distance of 5, but when they're going 0.6 times the speed of light, they're actually only going a distance of around maybe 4 or 3.7. So we could see that space-time actually dilates as we get closer to the speed of light. And this is a parabolic equation if we were to plot it on a graph. And this is also a diagram of how it would be, for example, for the spacecraft itself on the right side. You could see that for the spacecraft itself, everything else seems compressed. But from our point of view, the stationary observer, the spacecraft seems compressed. This is due to relativity. Okay, next.
Okay, here we have the first task of our study case, which is to calculate how much the spaceship contracts according to Bob. So basically, here we have the equation that is applied, which is called length contraction formula from Einstein's relativity theory. It states that an object moving at high velocity relative to an observer will appear shortened along the direction of the motion. And here we have L, which is the length measurement of an observer moving relative to the object being measured, and L0 being the length measurement of an observer at rest relative to the object being measured, and V is the speed of the object or the observer, and C is the speed of light. And the next problem, we have to explain why Alice and Bob disagree on the ship's length. And here, moving with the spaceship, Alice sees at its full length in 100 meters because she is in its rest frame, while Bob, stationary at the space station, sees the spaceship as shorter, which is 31.2 meters, due to relativistic effects. Next slide.
Okay, on this slide, it's almost the same like the previous one, but we changed the number of the speed, the velocity, where the previous one is 0.95, and in this case, we changed it into 0.99, which is a 99% of velocity speed. The step is also the same, where it is 0.99 c per c square, and we cross the c, which results the final answer 14.1 meter. And then next we discussed how line contraction affects high speed travel. So when objects are traveling near the speed of light, they appear shorter to observers who are not moving. And secondly, the spaceship remains the same size for the astronauts on board. And thirdly, this phenomena is important for future travel and particle physics, such as muons in cosmic rays. And lastly, spaceship will drastically reduce in length as relative speeds, which will affect navigation, engineering, and how time and space are perceived. And that's it from us. Thank you for listening to our presentation.